right, welcome to the topic of recursion. Recursion is one of those things that beginners oftentimes get really scared about, and maybe if I say that, you're already going to get scared about it. But it's one of the probably most elegant ways to solve problems in computer science. And so it pays to really understand at least it at a fundamental level what it is and what it does, and then try to solve a few basic problems with it. Now, whether or not recursion is something that you'll be using often, I wouldn't worry about it too much early on in terms of practical use, but it is oftentimes very popular to have programming problems that can be solved most elegantly with recursion. So it's helpful to know it, it's helpful to understand what it means and what it does. So in this lecture, we'll talk about the definition of recursion, we'll talk about the call stack, and then we'll do an example with counting down numbers, an example with factorial numbers, and then we'll talk about recursion with arrays and strings, and then tips for approaching recursion problems. So what is recursion? Recursion is when a function calls itself. And it's funny to me because I often think that functions, we write functions all the time that call other functions. And that doesn't scare, surprise, or concern anyone. But when you write a function that calls itself, all of a sudden everybody loses their mind, right? It reminds me of that scene in the Batman movies where the Joker is like, one thing happens and all of a sudden everyone's losing their mind. And I always think with recursion, it's what happens. Like, it's just the same thing you're doing. You're calling a function inside of a function. It just happens that the function is itself, right? And that adds a little bit of subtlety, but is not that different than calling a function. Recursion is a common alternative to iteration, right? Iteration is just using a for loop or a while loop. It's just another way to solve a problem of a for loop says, let me go over all the things in this set of things. And recursion is, let me handle this thing and use myself to solve the subpart of this thing. So in the real world, you'll see recursion in a few different places, right? So you'll see recursion replace iteration when it's easier, it makes the problem easier to reason about. Right, so if you have a big problem, and a good way to define that big problem is as solving smaller parts of that problem, recursion is a great way to solve that. It's sometimes used when it's easier to read than an iterative solution, and it's sometimes used if it's a good way to, or it can use, recursion can use a lot of memory, so if in certain scenarios it uses, when it doesn't impact memory usage too much, people might use a recursive solution that's more elegant than a iterative solution. So to understand recursion, you have to understand something called the call stack, all right? And the call stack is what we refer to as a function call stack, right? As functions call each other, they are putting their scopes, their variables onto a stack. So JS is single-threaded, so only one function can be running at any one time, right? And the call stack is the structure that JavaScript uses to figure out which function is running and what it can see and what happens when the function exits. So whenever we call a function, we add that to the top of the call stack. So a stack is, you can think of like a Jenga, like a stack of blocks, right? So you call a function, what you're doing is JavaScript is creating, the scope, the parameters, all that stuff. It's putting it into a block, putting into, this idea of a function call and putting it on top of the stack, right? So when we call a function, JavaScript makes all these things for us and puts it on top of the stack. And JS will start executing whatever function is at the top of the stack. So when the function goes on there, JavaScript starts executing the code along with all the parameters and local variables that are defined. So for example, we'll create a function first that console logs I am first, a function second that console logs I am second, then we call first and we call second. Now you notice here, first is being called and then second is being called. They're not calling each other anyway. So what we expect is that when first is called, on line 13, JavaScript creates the things that first needs to run, right? So it creates first doesn't have any variables, parameters, so it just pretty much creates an empty scope, and it puts it on top of the call stack. And the call stack looks like first, the console logs I am first, and then the call stack, and then when first stops running, the call stack is empty again, right? So as soon as first stops running, it gets pulled off the call stack. Then when second starts running, it gets put on the call stack, it's run, we get I am second, and then it comes off the call stack. So let's look at another example. Here we have a first function. It console logs I am first, and then it calls second, and then it says first is finished. Then second is called, and second just says I am second. So what happens here? When we call first, Let's look at our call stack. So first comes in, first is put on the call stack, we start running. We get an IM first from the console log on line 2. Then second is called, and so you see second is on top of first in the call stack, right? Because first is not finished, but second is now in charge of JavaScript running. So now second is called, we get an IM second, and then second returns, or second finishes in this case, and it gets pulled off the call stack. And you see how first was paused while second ran. So first is still on the call stack, and now it's going to finish running. First is finished, right? And then it's going to come off the call stack. So the call stack in B is high as the number of nested functions are being run. Okay, so now that we understand the call stack, let's look at an example of counting down numbers, right? So if we want to take a function that takes a number and counts down to 1, we can very easily do it with this for loop, right? Let I equal to the number, I greater than or equal to 1, I minus minus, and just console log out I, right? Easy peasy. We count down 5, we're going to get 5, 4, 3, 2, 1, right? So this is an example of the iterative version using the for loop to do something counting down. Okay, now let's refactor this to write the function that takes a number and logs it out. So here we count down, just console logs out num, and then we call console log on countdown on 5, we just get 4, 3, 2, 1. We can do the same thing without using any loops, and we'll get the same results, right? So here we're passing countdown 5, and then we pass countdown 4, we pass countdown 3. And so we're achieving the same thing as we did in the previous one, but we've in essence handwritten out the loop. So it's not great because we have to, this is not generalized code, right? We can't count down any number, but now countdown can output the number that it's given. So this will do the same thing. So now what we did is that every time we called countdown, we lower the number that from previously. So what here is that instead of having ourselves call countdown, what if we have countdown call itself, but subtracting the number each time it does that, right? So here we have function countdown, takes a number, outputs it, and then calls countdown with num minus 1, right? So now it's doing the subtract 1 instead of us doing it ourselves manually. And then we call countdown of 5, here's what we get. We get, of course, countdown of 5's on there, and we'll get a 5 out. Countdown of 4's on there, right? So countdown of 5 is still there because countdown of 5 is not finished. It called countdown of 5 minus 1, which is 4. And we get a 4, 3, 2, 1. Okay, now we're finished, but countdown of 1 outputs 1, and then it's going to do countdown of 0. We'll get a 0. We're not finishing the countdown. So this goes on and on until we get something called a range error, which a range error just means that we've made too many calls to the call stack, right? And so the call stack size is too large, and JavaScript will throw an error because oftentimes when the call stack is too large, it represents us having done some kind of recursion incorrectly. Okay, so now let's finish this because that idea is cool, right? We're able to have countdown call itself and do what the for loop did, almost in a more elegant way, but we weren't able to actually get to work properly. So our function called itself every time, but it called itself infinite amount of times. So this is the first problem that you run into recursion, in that if a function calls itself, you get into a very dangerous position where you can get an infinite loop very easily, because if it calls itself, then of course that can happen over and over again until the end of time if the call stack could be infinite. So now let's write a stop condition in our function that will stop it from calling itself, right? So in countdown, it should say, if I need to go down, I'll keep calling myself. If not, I need to stop and then let the whole thing unwind. So here with countdown, we'll have a stop condition. Now this is oftentimes called the base case, right? The base of all the cases that can be handled. Now we say if number is less than 1, we'll say I'm done. And then recursively, so if we do want to do more stuff, we'll output the number and then call ourselves countdown num minus 1. Excuse me. So then we call countdown 3. What we get is we'll get countdown of 3, outputs 3 because we're in the else case here. And then that will of course count countdown of 2, output 2, countdown of 1. It'll output 1, and now I'll call countdown of 0, and 0 is less than 1, so output's done, does not go into the else case, and it starts unwinding, right? Countdown of 0 finishes. Now countdown of 1 was paused on line 9. Now it also finishes, right? And so now we're done. So this is an example of a recursive solution to counting down numbers. Now, many people say, well, why bother with this, right? Why not just use a for loop? The first argument is that you can think of this as a more elegant expression of what it means to count down numbers, right? Rather than get caught up in the details of the for loop, to us, now we say counting down is outputting a number and then having myself output the lower number. So the way you're expressing it is simpler. But I mean, oftentimes it's not clear with something so simple. But let's look at the takeaway, right? One, you have to define a base case for when the recursion stops. If you don't define the base case, we get what we call a stack overflow, right? The stack getting too large, the call stack being too large. And second is that in the recursive case, you have to change the input in some way that you're getting closer to the base case, right? Because we can still very easily get an infinite loop if we never trigger that num less than 1 case, right? So for example, if we were doing a countdown and the countdown wasn't getting closer to, let's say the countdown was actually like a count up and that base case was defined as num less than 0, then we would also have the same error, right? We would never finish the recursion. Okay, so now we understand how to have a set of functions that call each other and output console logs, right? But now things get more complicated when functions return a value, right? So we say, okay, you know what? Don't just output console log, but actually return me something, return me some information, right? And so here, let's start by thinking about, okay, let's start by defining a base case. So in recursion, the first thing to think about is what are my base cases? And base cases oftentimes are what happens when you have the most simple input that expresses the simple versions of that problem, right? And so, for example, the sum of a single number is that number. The sum of many numbers you could define as, if you say, let me sum up many numbers, right, in an array. You could, of course, say a for loop to iterate through the array, but you also define that as a problem of, let me take the first number and then add it to the sum of the remaining set of the array, right? That would be the recursive definition. And then, of course, we test that that base case works before we start thinking about the recursive case. So a very canonical example here is factorial. So let's define a function factorial that takes a number and returns a factorial of that number. So just a reminder what factorial is. In mathematics, we define factorial as using the exclamation mark. And factorial really is just all the numbers of that number multiplied by all the numbers down to 1. Right? So, for example, 3 factorial is 3 times 2 times 1. Right? So 3 factorial is 6, 4 factorial is 24, 5 factorial is 4 factorial, 24, times 5, right? Which is 120. Now factorials grow very quickly, as you can imagine, because they're multiplying each time. And it's, we can calculate them. Of course, we can think about how we calculate this using a for loop, right? If a factorial of 5 is just, for 5, have a variable, the product, and then for 5 down to 1, product equals product times the current number, right? So we can define it with an iterative loop, but let's think about how we can do this with a recursive loop. So what are the simple outputs and inputs here, right? What are our base cases? So here, if we look at the inputs, we say like, well, 2 base cases we have that are pretty simple, almost by definition, are 0 factorial and 1 factorial, right? Both of those are just defined in factorial as being 1, right? Because 1 doesn't go down anymore. It's already the base case for itself. And 0 is almost by definition what happens. It's a definition of factorial. So we define factorial of 0 as being 1. So here we'll say, okay, let's define the function factorial. And we have a base case. If number is 0 or number is 1, just return 1, right? And then if we call factorial of 0 and factorial of 1, we should expect to get 1 on both ones, right? So that's good. We have a base case now of what factorial is. So we've set the base case. Now we have to remember that as we think about the recursive case, that num gets closer and closer to approaching a base case, right? So to approaching 1 or 0, so that we eventually hit the base case. So recursive cases have to approach the base case, right? You can think of this in mathematics as converging towards a solution, right? If you're diverging from the solution, then you get that infinite call error. Okay, so here we have a very interesting pattern, right? For a factorial can be defined as, our factorial of 5 can be defined as 5 times the factorial of 4, right? We don't have to necessarily know what factorial of 4 is. We just know that 5 times factorial of 4 is the definition of factorial of 5, right? And that's all the way down. That 4 is going to be, factorial of 4 can be defined as 4 times the factorial of 3. So here, let's think about the recursive case, right? We're getting closer to 1. So what are we supposed to do? Now, we should write this recursive case using the simplest possible input that would result in a factorial call, right? So, for example, if result equals, in fact, the first thing you should test is what is factorial of 2, right? Because that's the next case here, right? Don't like think about what a factorial of 100 is. Just think, what is factorial of 2? And let's console that result out, right? So, of course, right now, it's undefined because factorial doesn't return anything, right? So functions that don't return anything, or functions that don't explicitly return something, implicitly return undefined. So here we're getting undefined. So now we know we have to call factorial in the recursive case, and we have to return a number, right? So if number is 2, what do we do if we call factorial with num minus 1, right? So we console log out factorial of num minus 1, and that here will get, if we do result equals factorial of 2, then, and we console that out, here we'll continue to get, let's think of what happens here. So factorial of 2 comes in and says, am I the base case? No. Well, then I'm going to console log factorial of 2 minus 1, which is factorial of 1, and so then that will return to us 1. And so we'll console log out 1, and then undefined, right? Because the console log on line 13, again, we're not returning anything from the factorial. So now we think, okay, now what do I have to actually return? So we know that 2 factorial is 2 times 1. So let's console log out 2, the num, times factorial of 2 minus 1, which is the definition of factorial. And here again, we get 2, which is the answer we want. Again, we're still getting undefined for the result because we're not returning anything. So now let's just figure out what we return. And we say, okay, we'll set the result to num times factorial of num minus 1 and just return that result. And now if we let result equals factorial of 2, and we console log that out, we should expect to get the correct answer, right? So here, we're thinking about two things here, right? In recursive cases, how am I approaching or converging towards a base case? And in factorial, it's just that we're lowering the number every time. And then in the final thing we think about is what are we returning? So here we're returning the result that we got, right? So line 9 won't execute until the factorial function on line 8 returns. And then once that result returns, we're going to have the answer that we want. Okay, so here we can just console log out the result, and let's look at the call stack. So as we call factorial of 5, we'll eventually get, of course we don't hit the base case, we'll get the return value result will be 5 times factorial of 4. So of course that calls factorial of 4, and we put that in the call stack. Call stack, that will put 4 times factorial of 3, that goes in the call stack. 2, factorial of 1, that hits the base case, right? And then that returns 1. And so then in factorial of 2, we get 2 times, and then factorial of 1 becomes 1 now, right? That expression now becomes the number 1 instead of the function call. Now factorial of 2 returns a value of 2, and then the expression factorial of 2 now becomes 2. Now factorial of 3 returns 6, and then we see the factorial of 3 expression becomes 6, and that returns 24 all the way up until we return 120, right? So here we're using the call stack to represent the iterations or the recursive iterations of factorial getting smaller, and then as the call stack unwinds, it's returning to us the answer that was figured out inside of each call of factorial. Right, so at some point, the call stack gets to the base case and says, now I can start unwinding and passing the answer back up on each level. Okay, so what are our takeaways there? 1, first think about your base cases, right? If you start recursion and you don't think about base cases, if you don't think about the base case first, that oftentimes will end you up in a situation where you're defining the subproblem incorrectly. Because there's a subproblem, you said, oh, here's a subproblem, and then you realize this way of thinking about the subproblem never approaches the base case. It doesn't converge towards an answer. Then use simple inputs and outputs to define those base cases, right? So once we have those base cases, test it using simple inputs that at least result in one recursive call, right? Because that makes it easy for us to debug, it makes it easy for us to think about. So in factorial, that was us trying to get, well, we have our base case of 0 and 1. So the next easy thing to try is factorial of 2, right? That's making one call down the call stack. And then we start testing our function against more complex inputs. And then the reason that this is a good way to approach it is that you don't want to keep running into, call stack exceeded. You don't want to have to be looking at a call stack of 5 or 6 calls and trying to figure out what's going on here. If you have a very simple base case and a very simple test case, you can more easily kind of reason about what is going on. Something else is that you can use recursion on data types in JavaScript. So for example, if you're asked to recurse through an array or a string, then your base case often is when that array, an empty array or a single length, or an empty string or a single length, or a string with length of 1. So for example, if you're trying to find the sum of numbers in an array, right, like the sum of the numbers in an array, let's say you have a sum of, or an array of 10 numbers. You say, what is a recursive way to sum up these numbers, right? Well, then what is your base case? Well, your base case is when you have one number, then the sum is that number, right? So for example, if the array length is 1, the sum is very easy to calculate. You don't have to do any addition. You say, by definition, with array length 1, my sum is this number. You can also say, the array length is 0, my sum is 0. My sum is 0. So that's two ways kind of define the base case. All right, so the base case requires that iterable, like the array or the object, to have a length of 1 or 0. And that means that for the recursive case, you have to reduce the length of the iterable, right? So if you're summing up 10 numbers recursively, every time you recurse, you have to make sure your array is getting smaller or getting closer to array length of 1, right? If you're not doing that, then you will never hit that base case, and you'll again have this Stack Overflow error. And now in our next lesson, we'll talk about nested arrays, which we're going to approach differently. And so that's what will be summing up all the numbers in nestable arrays is a great use of recursion because, we'll see in the next lesson. So some more hints around recursion. Start with the base case, right? Always think, what are my base cases here? Because if you can't define a base case, you can't solve this problem in a recursive way. Test them with simple inputs, so that will only result in one recursive call to the base case to make it easy to reason about. And you oftentimes think about, what is my function returning, right? Because the base case will, by definition, return something up, right? Either return or end, but whatever it's returning is going to be what all of the other recursive cases are going to return. And it's what it's returning helping you get closer to the answer, right? So your recursive case and your base case should return the same thing. Otherwise, you really can't, you can't use recursion to solve that problem because you can't recurse down to a base case, return one type of thing, and then return a different type of thing up the chain because you won't, those two things, that won't mesh in the recursion. And in recursion, I highly recommend using console log or debugger to debug. So I'll show a quick example of using debugger to look at the call stack. All right, let's do that right now. Let me do a recap and then we'll do a quick code sample. So for recursion is just functions calling themselves to solve problems. To understand recursion, a recursion and the call stack are intricately related, right? Recursion uses the call stack to store information and then unwinds the call stack to pass up answers, to higher members of the call stack. We looked at an example here of counting down numbers, both iteratively with a for loop and using recursion. And we looked at the same thing for factorial. They're very similar. And the two things to be careful about is that both of those had to have a base case or they would get infinite call stack exceeded errors. Recursion is great for arrays and strings, or it's possible with arrays and strings where your base case often means an empty array or an array of one element. And we looked at a few different tips for approaching recursion problems. Defining the base case, defining the simple recursion, and then thinking about what is coming up, returning from each iteration of that recursion. All right, let's look at a quick example. We'll do factorial, and we can see what that looks like in debugger. Okay, so let's look at a code example here for factorial. So here, I am going to create a function factorial. And that will take a num. And let's define the base case here first, right? So base case. So that base case will be if num is equal to 1 or num is equal to 0, then I'm going to return 1, right? That's by definition. And let's just console log out the factorial of 0 to test that. and factorial of 1. All right, so if I run this, okay, I'm getting 1 and 1. Now if I log out factorial of 2, I get 1, 1, and undefined. So 1, 1, undefined. Exactly what I expect. Okay, so here what I want to do is talk about the recursive case, right? My recursive case. In recursive case, what I want to do is create a result and do my num times the factorial of my num minus 1, right? And if I try this, again, I'm still going to expect to see 1, 1 undefined because I'm not returning the result. So if we return the result here, run it again, and now I'm getting 2. So now let's look at this if I do console log factorial of 10. So that's a pretty big number. I run it. Okay, so that gets us something like 3.6 million, all right? Now let's look at what the call stack looks like when this happens. So I'm going to put a debugger here. And start debugging this. So I'm going to debug, start debugging in Node.js. All right, so here you can see, let's look at our call stack. So it came out of the, like this anonymous function is kind of the general space of this factorial, the global scope of this factorial, and then factorial here, it was called with num0, so this is our first case. This is, you know what, let me stop this and just call factorial of 10. Okay, I'm going to call factorial of 10 in Node. So now num is 10, the call stack has just 1 factorial. Now if I play this, you see here now num is 9, 8, 7, 6. So the num is not that interesting. What is interesting here is looking at here, the call stack. So you see here, all of those factorial calls are still sitting here on the call stack. And the next thing with the debuggers, I can jump to any point in the call stack and see what's going on, right? Now let's actually walk through the steps. So here, num is 6. Of course, that won't pass if. And then it says num is 6 here, and it's going to call factorial of 6 minus 1, which is 5. You see if I go into this step, I'm now getting to factorial of 5. And then this forces this debugger, and keep going. So I'll keep playing this out. Factorial of 3, 2, num and 1. Right, so now this if case will be true. I return 1. I'm going to press this button here, which means step out. And now here the result is the first result, 2, because factorial returned 1, and num here was 2 that called it, so this is now 2. I'm going to step out again. Now this result will be 6, because the result is, this num was 3, right? Factorial of 2 now becomes 2. And if we keep stepping out, we'll see that result is capturing the answer, and num is, num is a good index of where we are, right? So, and result is capturing that answer. Until we go all the way up the call stack. You see the call stack unwinding on the left here? Until we get the first call of our call stack. Result here is already the 3.6 million that we defined. This returns up, and now we're back in the console log. And we play this here. And now we'll get the answer we are, 3.6 million. So you see, in the debugger, we can actually see the call stack, being built up and then unwinding off of the, as the results are figured out. As you approach the base case, the call stack builds, and as you hit the base case, then the call stack starts unwinding down. All right, I hope that was a useful introduction to recursion. Again, it's one of those things where beginners oftentimes struggle because they have a hard time identifying base cases and then identifying the recursive case. That's totally acceptable, and you don't have to be that, don't worry, if this whole thing is lost on you for now, don't stress out too much. It's not required to succeed in programming in your early parts of programming. It's really just a very elegant and interesting way to approach problems, and so we'd like to show you not only how to think about recursion, but how to solve problems with recursion early on. Okay, and in the next unit, we're going to talk about recursion with different types of data structures and look at some of the things we talked about earlier of how do we recurse over things that are nested, like nested arrays, etc. See you then.